Deep inside the Arctic, near 70 degrees north, a freight train pushes through a blizzard across the Yamal Peninsula, minus 50 degrees Celsius. Snowdrifts threaten to bury the tracks. 572 kilometers of rail lie over permafrost that wants to swallow it whole. This is the northernmost railway on Earth, and Russia did not build it for passengers or prestige. Beneath this tundra sits 5 trillion cubic meters of natural gas. Extracting it required engineering no one had ever attempted, a workforce surviving in total isolation, and the will to succeed where Stalin's railway of death failed. Beneath the Yamal Peninsula's frozen crust lies an economic engine of staggering scale. Reserve auditors working with seismic data and core samples have certified the Bovinenkovo gas field at 4.9 trillion cubic meters, enough to supply Europe for decades. On spreadsheets in Moscow and Zurich, that figure translates to a projected net present value of $12 billion US, calculated over a 30-year horizon with an 8% discount rate. Every cubic meter of gas that reaches the market is profit, but only if it can be moved reliably out of the Arctic at industrial scale. The sheer volume dwarfs any local infrastructure. At peak, Bovinenkovo produces over 100 billion cubic meters of gas per year, feeding not just Russia's domestic grid, but also export pipelines stretching west to Europe and south to Asia. Without a permanent, high-capacity overland artery, the field's output would choke on its own isolation. Seasonal ice roads and river barges cannot deliver the 10,000 tons of pipe, 5,000 tons of steel, and 2,000 tons of drilling equipment needed each month to keep the gas flowing. The cost of relying on icebreaker convoys through the Kara Sea would erase profit margins and expose exports to global shipping volatility and sanctions risk. Gazprom's internal cost-benefit models, presented to federal backers in 2007, put the capital cost of the railway at $5 billion US. That sum covered 572 kilometers of track, permafrost-compatible foundations, and the 4-kilometer Urabay Bridge, a single structure that alone accounted for $450 million. Every kilometer added expense, but every kilometer was necessary. Sensitivity analyses showed that even a 10% drop in train frequency would raise per-ton transport costs by 15 cents, threatening the entire project's economic logic. The railway, in this calculus, is not an accessory, but the backbone. Without it, Yamal's gas is stranded and Russia's energy ambitions stall at the water's edge. State financing arrived as a federal loan package of 200 billion rubles, funneled through a Gazprom-owned rail subsidiary. The line's completion unlocked the rest of the Yamal mega-project, accelerating pipeline construction, attracting foreign capital, and anchoring Russia's claim to Arctic resources. The railway was not built for spectacle. It was a calculated response to the hard arithmetic of energy extraction, a multi-billion-dollar bet that only made sense when every ton of steel, every trainload of gas, and every ruble of return was counted. The story of the Northernmost Railway is not about enduring the Arctic for its own sake, but about making the Arctic's hidden wealth move, on schedule, at scale, and in defiance of the elements. Obskaya sits at 71.47 degrees north, a remote junction where the northernmost railway on Earth begins its journey into the Arctic interior. From this outpost, the line carves a deliberate path across the Yamal Peninsula, shaped not by the shortest distance, but by the logic of survival and extraction. Every kilometer had to be justified, financially, geologically, and logistically. The planners faced a landscape riddled with wetlands, shifting river deltas, and permafrost that thaws and swells with the seasons. Satellite imagery and decades of field surveys revealed that only a narrow coastal corridor offered ground stable enough to support heavy trains year-round. Deviating just a few kilometers east or west would have plunged the line into bogs or thaw lakes, where even tracked vehicles sink during summer. The route's most formidable obstacle is the Urabe River. At its floodplain, the river stretches into a 4-kilometer-wide expanse of braided channels and ice-clogged marshes. Here, engineers designed one of the world's longest permafrost bridges, a stone-filled causeway that stands as both a technical milestone and a financial gamble. The bridge alone cost $450 million, nearly a tenth of the entire project's budget, but without it, the railway would have dead-ended. Beyond the Urabe, the line threads north, skirting the edge of protected tundra and avoiding the largest wetlands identified in Soviet-era geological maps. The alignment was chosen to minimize environmental disturbance, but also to reduce construction risk. The permafrost here is continuous, but its thickness and ice content vary unpredictably. By following a corridor of relatively high, well-drained ground, the railway could be anchored on embankments and piles without constant fear of thaw settlement. Short sidings and service yards dot the route at intervals, with the largest at Karasave, where a future spur will reach new gas fields. But the backbone remains the single main line, built for freight but capable of moving people and supplies in any season. At these latitudes, the sun can vanish for weeks and the wind can erase all traces of a track in a single night. Yet every switch, bridge, and kilometer of rail is a calculated answer to a specific challenge posed by the Arctic. The path of the Obskaya-Bovanenkovo line is not arbitrary. It is a map of constraint and opportunity, a physical translation of energy strategy into steel and stone, designed to keep the gas moving no matter how the tundra shifts beneath it. Frost is not just a backdrop on the Yamal Peninsula, it is the ground itself, a living, shifting force that can swallow steel and stone. Every meter of the Obskaya to Bovanenkovo line is an engineered argument against that threat. The railway's chief track engineer recalls the first core samples drilled at Karasave, ice lenses layered between silt and gravel, ready to swell and buckle with the smallest rise in temperature. The challenge was clear. If the permafrost beneath the rails thawed, the entire artery could twist or collapse, severing Russia's link to its Arctic gas reserves. The fix begins at the base. Beneath the rails, a 0.6 meters layer of crushed stone and gravel forms the embankment's backbone. This granular base, screened to 30 to 50 millimeters, is not just for weight bearing, it drains meltwater away from the frozen ground and slows the penetration of heat from above. Over this, a 0.4 meters silty clay fill is compacted to a density of 1.85 grams per cubic centimeter, sealing out moisture and stabilizing the structure. But insulation is not left to chance. Engineers roll out a geosynthetic blanket, polyethylene filled with silica aerogel, directly over the embankment, creating a cold shield that blocks heat transfer from the sun and train wheels alike. Still, the Arctic is relentless. Freight trains, each axle pressing down with 30 tons, pump warmth into the earth with every pass. To counteract this, the line is studded with 210 vertical thermosiphons, copper-lined ammonia pipes, each 12 meters deep, spaced at 7-meter intervals along the most vulnerable stretches. When winter air plunges below freezing, the ammonia inside these pipes vaporizes, rising to the condenser above ground, where it sheds heat to the atmosphere and condenses back to liquid. Gravity pulls the cooled ammonia down again, drawing heat out of the permafrost in a silent, passive cycle. This is not brute refrigeration, but a perpetual energy-free siphoning of warmth away from the ground, preserving the frozen base beneath the tracks. Critical structures, bridges, sidings, and station platforms rest on concrete piles, 1.2 meters wide and driven 15 meters into the permafrost. Laboratory tests show that the bearing strength of these piles drops by 80% if the ground temperature rises from -3 degrees Celsius to -0.3 degrees Celsius. Thermosiphons are clustered even more densely around these points, forming a defensive ring that keeps the foundation locked in ice. The stakes are not theoretical. The loss of bearing capacity here could mean a sudden bridge tilt or a sunken turnout, halting gas trains and jeopardizing billions in export contracts. The installation process is as meticulous as the design. Construction teams unroll the geosynthetic blanket first, then compact the granular base and silty clay fill in layers. Thermosiphon bores are drilled before the embankment is closed, ensuring each pipe is seated flush with the frozen strata. Only after the embankment settles within a 30 millimeters tolerance do crews lay the ballast and weld the rails, finishing with a laser-based track geometry system that can detect settlement shifts as small as 2 millimeters. The chief engineer sums up the logic. Every hardware choice, from the thickness of the insulation to the number of thermosiphons, is a direct answer to the physics of thaw. The railway's survival depends not on stubbornness, but on relentless adaptation, a system designed to read the ground, respond to its changes, and hold the line in the face of a warming world. The result is a corridor where theory becomes hardware and survival is measured in degrees, millimeters, and the steady year-round movement of gas and steel. A train in the Arctic does not simply run, it is kept running every hour by a web of sensors and human vigilance. Along the Obskaya-Bovenenkovo line, maintenance is not a periodic event but a constant living process. Under the trackbed, digital thermistors and pressure sensors feed a real-time stream of data into Gazprom's central control room, where operators monitor ground temperature, frost heave, and snow accumulation. This digital twin, a virtual replica of the railway's physical state, predicts trouble before it strikes. If the ground temperature at any point rises above -1 degree Celsius for more than 30 days, the system triggers an automated work order. Crews are dispatched to reinforce embankments or adjust thermosiphon cycles, sometimes in the middle of a snowstorm, because a single missed alert could mean a buckled rail or a sunken bridge. Winter is relentless. Snowfall on the Yamal Peninsula averages over 1.5 meters, but wind can pile drifts twice as high in a matter of hours. The snowplow commander, one of the most experienced on the line, describes a typical storm. Visibility drops to 10 meters. The rotary plow blades are chewing through ice at 30 kilometers per hour, but the drift closes behind us as fast as we clear it. We run in convoys, 2 plows, a support wagon, and a heated crew car. If we stop, the train will be buried in less than 40 minutes. Each snow-clearing run is guided by sensor alerts and weather station data. When a blizzard is forecast, the digital twin calculates which sections are most at risk of blockage and dispatches plows accordingly. The average snowplow speed, 30 kilometers per hour, can drop to half that in heavy ice, stretching a 12-hour shift into an 18-hour ordeal. The budget for this work is not trivial. Annual upkeep for the line, including emergency repairs and snow clearance, averages $9.4 million. That figure has risen nearly 20% since 2017, a direct result of more frequent and severe storms linked to Arctic warming. The rising costs are a constant factor in decisions about maintenance and traffic. Storm protocols are drilled into every crew. Each train carries insulated survival kits and satellite beacons. If a plow is immobilized, the crew has instructions to seal the cabin, switch on emergency heaters, and wait for rescue, sometimes for hours, sometimes for a day. The snowplow commander's voice is matter of fact. You do not fight the Arctic, you respect it, or you lose. These are practical rules of survival. Digital twin operators working from heated offices in Obskaya are as critical as the men in the cabs. Their screens show a living map of the railway, color-coded for risk. When a sensor detects abnormal thaw or a track section begins to settle, the operator can reroute trains, slow traffic, or order a maintenance convoy out before the problem escalates. It is a delicate balance. Too little intervention and the line fails. Too much and the cost spirals beyond what the gas field can support. Operators make choices measured in millimeters and minutes. Every freight run is the product of this perpetual effort, an interplay of machine, data, and human resolve. The railway endures not because it defies the Arctic, but because it adapts to it, hour by hour, storm by storm. The result is a system always on the edge, its survival measured in millimeters of frost, minutes of lost visibility, and millions of rubles spent to keep the gas flowing north to south, no matter what the weather brings. 16,000 workers keep the Obskaya-Bovanenkovo line alive, their lives rotating in and out of the Arctic's grip on a schedule as relentless as the seasons. The shift foreman at Bovanenkovo describes the rhythm: 12 hours on, 12 hours off for 2 weeks straight before the long train south returns him to warmth and family. Barracks at Obskaya, Labitnangi, and Bovanenkovo are more than shelter. They are islands of light and heat, stocked with satellite internet, hot meals, and a gym where men and women try to shake off the monotony. But outside, the wind scours everything, and frostbite is a constant threat. Every third worker has felt the sting, hands numbed during a track inspection and cheeks burned raw by the wind. The premium pay draws them north, but isolation leaves its own mark. Company psychologists fly in each month, meeting with crews who speak of homesickness and the strange quiet of the polar night. Beyond the rail embankment, the Nenets herders move their reindeer along ancient corridors that now intersect the steel artery. The Land Use Agreement, license number I-08-2015, spells out the rules. 5 migration corridors, each protected by removable crossing bridges, and a legal right to halt trains if a crossing is damaged or blocked. Gazprom pays annual compensation to Nenets communal funds, but money cannot replace the freedom of a landscape unbroken. Nenets elders meet with railway managers each spring, negotiating train schedules to avoid the peak migration window when 12,000 reindeer must pass. Environmental monitors from the Institute of Arctic Biology walk the line each summer, measuring the grass, counting the calves, and watching for signs that the ground is shifting under the weight of both steel and hooves. In this shared landscape, the railway is not just a line of commerce, but a thread binding together the fortunes and the vulnerabilities of those who work above the permafrost and those who have always moved across it. The human story is written in rotations, crossings, and the uneasy coexistence of modern industry and ancient migration. A few kilometers north of the modern rail artery, the tundra conceals the rusting bones of another project, a line that never reached its destination. In the late 1940s, Stalin's government ordered the Salakard-Igarka Railway, a 1,300-kilometer vision meant to bind the Arctic coast to the heart of Siberia. The reality was a forced labor corridor built by tens of thousands of Gulag prisoners driven north with picks, shovels, and little else. Winter temperatures fell below -50, and the permafrost swallowed tools, rails, and men alike. By the time the project was abandoned in 1953, at least 12,000 workers had died, and some estimates run far higher. The line's remains, warped tracks, and collapsed timber trestles still surface each summer as the ground thaws, mute evidence of a strategy that valued output over lives. A local historian walking the ruins describes the difference in a single word: purpose. The Salakard-Igarka line was born from ideology and coercion, not economic necessity. Prisoners were expendable, the ground misunderstood, and the project's only metric was speed. There was no market calculation, no return on investment, just a drive to conquer the north at any cost. Today's Obskaya-Bovanenkovo line is a product of capital, not command. Every kilometer had to justify itself in rubles and cubic meters of gas. Workers are paid, not compelled. Engineering decisions answer to geology and thermodynamics, not a dictator's timeline. The contrast is not just technical, but moral. Where the old line left a legacy of graves and abandonment, The new railway endures because it serves a clear economic logic. The energy that moves through its arteries is measured in profit and power, not in lives spent. The ruins of the Railway of Death remain, a warning embedded in the permafrost, a reminder that Arctic ambition without reason or restraint will always founder on the ice. Here, steel rails cut through tundra not for glory, but for gas, fueling economies far beyond the Arctic Circle. The answer to why this railway exists lies in global energy hunger, not heroics. Today, as the world races to tap new frontiers, every kilometer exposes the tension between resource ambition and environmental fragility. In the north, infrastructure is never just engineering. It is a test of what we are willing to risk. Share your thoughts below.